Okay, in this quick video tutorial, what we're going to look at is the concept of length contraction. A consequence of the speed of light being constant and invariant for all observers as measured from an inertial reference frame, that's a non-accelerating reference frame. The fact that the speed of light is invariant and always moves at 3 times 10 to the 8 meters per second, regardless of your relative motion. We see that another consequence of this, besides just time being dilated for an observer watching an event or the simultaneity of event not being absolute, we also have to realize that now length is also not an absolute concept. So measurements that people make in different reference frames are not the same. So this means that space and time are not absolute concepts anymore. And in fact, only the speed of light is the constant in this. And the consequence of that is that we must allow space and time to contract and warp. Because time's warping, if length didn't contract, we would actually run into very real physical discontinuities or so basically what we're going to look at now is a derivation of how much, or figuring out how much length contracts based on the motion of an object and what it looks like in different reference frames. Because again, even though you measure two different things in two different reference frames, both are correct. And again, because we move so slowly, we often don't notice these contractions in space. And when I say space, I mean literally the distance between you and other objects, and walking towards things, and running towards things, and moving a car towards things. So what you're going to do is clearly you're just going to download this file here. This is the length contraction note. And then I handed out these special theory basic problems, so all of them, so you can do the time dilation and length contraction as well. We'll get into mass dilation later. Okay, so let's get to this. And there we go. Okay, length contraction. What we see here is a ship, and this ship is traveling from planet A to planet B. The distance between the two planets is LS. Okay, and we're going to call this now. This is different than the other one. It switches, which is a bit frustrating, but at the same time we have to deal with it. This is the proper distance. This is the distance that a person just looking at these two planets from afar says, oh, planet A to planet B, here's the distance. And this is the proper distance. We're not moving with respect to it. So when I say proper distance, I say it's measured by person watching the motion or watching the event. So I'm watching that ship fly by. So I would physically get out a ruler and measure that distance by some point. A stationary observer watches a ship fly by. This ship is moving at a very, very fast speed. In fact, this fast speed is, approaching the speed of light. In fact, any speed will do it. It's just that we won't notice it. All right, well, let's take a look at the times that we might measure in these instances. Well, an observer measuring the time, we know, is going to measure the dilated time. Okay, so we know that's true. We've already worked this through. Dilated time. So they're going to say it takes 10 seconds to get there or something like that. And that's the dilated time, because they know the person in the ship is going to measure a smaller time, the contracted time, or in this case, the contracted time. So we're going to measure the 10 seconds maybe, and they're going to measure maybe 6 seconds, right? Because the delta TS is going to be smaller. Well, to find out how long it would take to travel from point A to point B is simply found by taking the distance that we travel, LS, and divide it by the speed of the ship. So if this was measured in kilometers, and this is kilometers per hour, the kilometers divide out and the hours comes on top, and we would get a time in hours. Or distance equals speed times time if I move that up. So this is just the speed equation, the average speed equation rewritten. So the amount of time it takes to get from there to there is just take that distance that we measured with a ruler or whatever we want, divided by the speed of the ship, and we say it takes X amount of seconds, hours, whatever to get there. No big deal. The moving observer, however, is going to see something a little bit different. So we already know that delta Tm is gamma delta Ts. Now we know gamma is just that funny little thing that we talked about before, and I'll kind of just scoot it up here. It's the 1 minus the square root of 1 minus v squared over c squared, okay? We know that. It's just simpler to write it this way. This is that annoying little factor that changes all of space and time for us. Because our v's are very small, this is typically equal to 1, or close to 1. It's never exactly 1, but you know, unless you're not moving. But it's close to 1, so we never really notice these time differences much, but it's there. So what we're going to do now instead is rearrange for delta Ts. Nothing tricky here, just go delta Ts is simply delta Tm divided by gamma. Okay. This here we called before the proper time. Now I know it's getting confusing of what's proper time and what's proper distance. They do change, but that's okay. The proper time is measured in the event. So this is from inside the event. Okay, so that'd be like, in this case, inside the ship. So inside the ship, they're going to take the time that you measured to go across from planet A to planet B, divided by the speed, and they're going to find that if you divide it by the gamma factor, however fast they're going, let's say the gamma factor is 2, you would take the time divided by 2 and you'd see it takes half the time. So the person in the ship is going to measure half the time. Well, what we're going to do now is we're simply going to say that, okay, well, delta Tm, right, is this. It's Ls over V. So we're going to actually see that it's Ls over V, and the gamma would stay there. We also know something. There's one other piece of information that we have. This is just substitution. We also know this, that if the person in the ship is measuring their time, but they want to measure it differently, they say, well, let's look at my distance that I traveled, Lm, not Ls anymore. This is the distance that the person in the ship might measure. So this person in here is traveling from A to B. They're not going to measure the same distance. We already showed that in the previous day, that if time shrunk, or if time was longer for the one, then the distance traveled is going to be greater. So we're going to take Lm, which is the distance that the person in the ship would see, and they know how fast they're traveling, so they divide by m. Well, now we know that we have a delta Ts here, and this is delta Ts. So therefore, a very quick substitution says that Ls over gamma V equals Lm over V. Very simply, you see that the V's divide out, and you get that, so this implies that Lm equals Ls over gamma. This is different than delta Tm equals gamma delta Ts, where that is gamma. We were dividing by gamma this time. Okay? So what does that mean? Well, that means that if I wrote this out, it would be Ls. 1 over gamma is, in fact, just that. So we end up with this equation that the distance the person in the ship measures is the proper distance, the one the person watching it, the actual measurement, or the measurement, not the actual, the measurement from A to B, multiplied by 1 over gamma, or this factor. And what's really interesting, of course, is that we know that this piece of information here is always less than or equal to 1. It's always less than or equal to 1, because no matter what, this small term, although it could be close to 0, it's 0 if you're not moving, and 1 minus nothing is 1, square root of 1 is 1. This tells us that Lm will always be less than or equal to ls. This is a huge concept here. So in our diagram below, you will see that the person in the ship measures a smaller distance between the planets. So they measure a smaller time, a smaller distance. So if you divide the distance by the time, you get the speed of the ship. The person watching the ship up here measures a bigger distance, a bigger time, but if you take that bigger distance divided by the bigger time, you get the same speed. And you have to, because we know the ship is traveling at that specific speed. And that's how you bring reality back into focus, if you will. You can't change the time without changing the length, which also means that space and time are intricately woven into one another. Einstein touched on this again 10 years after writing his initial papers on special relativity, when he wrote his papers on general relativity, where he looked at what gravity is. So the length contraction equation, as we just pointed out, is Lm equals Ls times the square root of 1 minus v squared over c squared. Or, if you like using the gamma stuff, it's Lm equals Ls over, that's gamma. Here you're dividing by the gamma factor, which makes Lm smaller than Ls, because gamma was always bigger than or equal to 1. So gamma is always bigger than or equal to 1, because 1 over gamma is always less than or equal to 1. Now, because of that, it means that you're always going to be dividing the proper length by some number. In some cases, it's just 1, and the two lengths are the same if you're stationary with it. This is what we call the contracted length. And it's the contracted length because it's going to be smaller than the proper length. So basically, as gamma increases, meaning we're going faster, this implies that the length will get shorter. Now, what does this mean? Well, it means if I put my pen on this page and I measure the length of this pen, turns out that if this pen was flying by this screen really, really quickly, right, and you were able to measure it, you would actually see this pen shorter than the pen actually is when it's stationary. You would also measure the time that it took to go by, like all this stuff, right? So you would measure it shorter. Now, what's interesting is that the length only contracts in the direction of motion. And this is hugely, hugely important. So the biggest sort of star you want to write here is that the contraction only occurs in the direction of motion. That means that if we're looking at a pen, right, it means that it would get shorter, but its width would stay the same. So if we're looking and thinking about that, it means that a circle moving by us would look more like an oval. So it would maintain its height, but it would get squished. A triangular ship flying by would just look like a squished triangular ship, depending on its direction of how fast it's going. Obviously, if it's not moving, it would just pop back to being looking like this. If it's getting close to the speed of light, it would look much more squished. If you reach the speed of light, it would become infinitely thin, which can't happen, so we don't worry about it. All right. It's a bit of a long video, but we need to get through this last little bit here and do a quick example. A meter stick is accelerated to a speed of 0.8 c. How long in distance would an ant living on the meter stick measure the length of the meter stick to be? And calculate the meter stick length as observed by someone watching the stick fly by. So question number 1, we know the speed of the ship, 0.8 c. Okay, if I draw a little meter stick here we go. Draw a little ant, so we know it's going to be, and there's a little ant on here. All right, there we go. And the speed of this thing is 0.8 c, maybe in that direction. Okay, so A, if you were an ant living on this thing, well, in the ant's frame, everything's fine. They would measure they would measure 1 meter. So if the ant walked from this end down to this end, they would conclude that the length of this stick was 1 meter. Because they're stationary with respect to the ship moving, or this meter stick moving. If they were talking about the distance that they're traveling, if this meter stick was traveling from planet A to planet B, the distance between planet A and planet B would be shorter than someone outside watching would see, which is fine. But on the ship itself, the ship would appear normal. Just like when we're on the Earth, we're moving with the Earth, all the measurements we make on this Earth seem normal. Someone watching our Earth go by actually sees a slightly squished Earth and slightly squished measurements. Our meter sticks don't look quite 1 meter in length. Now, we're not moving fast enough to really see that, but that would happen. It is happening. B, let's find the contracted length. So now we're going to watch this ship, this meter stick, fly by. Okay, well, what's the proper length? Well, we know that if this object stopped moving, a meter stick is 1 meter in length. Okay, and we know that the speed is 0.8 c. Because we're in the c units, it's very easy just to write 0.8 squared instead of doing all the other calculations, which just make it more difficult. And what we find when we plug this into the calculator is we get 0.6 meters. So we would actually measure it to be only 0.6 meters. Now we would still see the 1, and we'd still see the 100 centimeters, we'd still see the 0, we'd see the 50, but everything would be squished. All the millimeters, everything like that, all the atoms, everything would just be squished up so that you would end up with this 0.6 meters overall. Even the ant would be a little bit narrower, but the height of it and the width of it would stay unchanged, just in the direction of motion. Another way to think about this is, we could calculate the gamma factor. And gamma is just 1 over the square root of 1 minus, in this case, 0.8 squared. And if you calculate that, you get a gamma of 1.67. And if you take 1 meter and divide it by 1.67, you get 0.6 meters, the same value. Time passing for this little ant is slower than we would measure outside. So even though it's shrinking, time's also changing. In part B, question number 2, an astronaut travels from planet A to planet B. The astronaut in the ship measures the distance between the 2 planets. So this is the astronaut on the ship. An observer from outside the system measures the distance between the planets to be this. Okay? Calculate the speed of the ship. what times would each observer measure the trip to take? Calculate the gamma factor as well. I feel like this question is backwards. I think what you're going to need to do is, when we look at this 600 million meters and this smaller distance here, these are backwards. The astronaut and the ship measures the distance between the two planets should be this. An observer from outside this system measures the distance between the planets to be this. So switch these two clearly, because it's not the correct measurement. So once you do that, calculate it and see if you can figure out the speed of the ship as well as the gamma factor. And then what you're going to do is work on the time dilation questions and the other two questions, which are the ones dealing with length contraction.